This line introduces the core concept. Using GroupShuffleSplit from Scikit-learn for cross-validation. Cross-validation is a technique to evaluate a machine learning model's performance by splitting the data into multiple folds. GroupShuffleSplit adds a crucial layer, ensuring that samples from the same group are kept together during these splits, preventing data leakage and bias. The problem sets the stage. We have 100 data points, divided into 10 groups of 10 samples each. We want to split this data into 3 training, testing sets, folds, for cross-validation. The key is that no single sample group should appear in both the training and testing sets of any one fold. This is vital to prevent bias and ensure robust model evaluation. This line simply indicates that the following lines present different configurations of the GroupShuffleSplit function, each of which will be evaluated as a potential solution. Option A suggests using 3 splits, with 20% of data in the testing set for each fold. Let's think about this. With 10 groups and 20 samples reserved for testing per split, 20% of 100. The risk of having a group split between training and testing is very high. Option B uses 3 splits again, but now 50% of the data, 50 samples, are in the testing set. Is this likely to maintain group integrity? It's virtually impossible to avoid overlap between train and test sets in each fold with this configuration. Option C proposes 10 splits with 10%, 10 samples, in the test set. Could this work? While theoretically possible to avoid group overlap, it's not guaranteed. A random split could still violate the constraint. Option D explicitly defines groups, using "NP. Repeat, NP. Arrange, 10, 10. Which means creating an array with numbers 0 to 9 repeated 10 times each, and uses 3 splits with 20% of the data, 20 samples, for testing. This explicit group definition and a careful choice of "test_size" allows the algorithm to guarantee that there is no overlap between training and testing sets within a fold. Okay, let's look at row 9 and 12 together. Row 9 tells us we have a dataset with 100 samples, divided into 10 groups, each containing 10 samples. Row 12 then starts to illustrate the grouping, beginning with Group 1. This helps visualize how the data is structured and is important for understanding how the GroupShuffleSplit will work. We need to make sure that the chosen method doesn't mix samples from the same group between training and testing sets. Row 10 and 14 continue this visualization of the dataset's grouping structure, ending at Group 10. Remember, all 10 groups have 10 samples each. This structure is fundamental to the problem because the goal is to choose a method that will keep the samples from each group together during cross-validation, either entirely in the training set or entirely in the testing set. Row 11, with the ellipsis, indicates that the dataset visualization continues in the same manner as shown in rows 12 and 14. In other words, there are 10 groups, numbered from 1 to 10, with each group containing 10 samples. It's a very clear and organized data structure, a fact that's vital for the GroupShuffleSplit algorithm to function properly. This section introduces the core concept, using GroupShuffleSplit from Scikit-learn for cross-validation. We're essentially setting the stage for a problem involving splitting data into training and testing sets while keeping groups of data together. The problem is to figure out how to split our data into 3 folds, groups, for cross-validation using GroupShuffleSplit. The crucial part is that we need to ensure no single group gets split between the training and testing sets within each fold. This is key for maintaining the integrity of the groups and avoiding data leakage. We have 100 data points neatly organized into 10 groups, with each group containing 10 data points. This structure is important because GroupShuffleSplit operates on groups, not individual data points. Our objective is to divide this dataset into 3 folds for cross-validation. The key constraint is that no single group can appear in both the training and testing sets for any of these 3 folds. Think of it like dividing a class of students into 3 teams for a project, making sure no friends are split between teams. Here are several different ways to configure the GroupShuffleSplit function. We need to determine which options guarantee that the previously stated condition, no group overlap, will be met. Each option represents a different way of specifying the parameters that control the splitting process. Option A sets the number of splits to 3 and the test size to 20%, 0.2. Let's analyze whether this configuration will certainly avoid any group overlap. Option B is similar to option A, but uses a larger test size of 50%, 0.5, potentially increasing the likelihood of group overlap. Option C changes the number of splits to 10 and uses a test size of 10%, 0.1. Let's see if this will guarantee no group overlap. Option D explicitly specifies the groups using "NP. Repeat, NP. Arrange, 10, 10, which creates a clear group structure for GroupShuffleSplit to work with. Let's investigate if it provides the guaranteed no overlap. The final goal is to select the options that are guaranteed to create folds where no group is split between training and testing sets. This requires carefully examining the implications of each option's parameters. Hey Vamsi, this sets the stage for our problem. We have 100 samples neatly divided into 10 groups, each with 10 samples. Our goal is to split these samples into 3 folds for cross-validation. Option A aims for 3 splits, with 20%, 20 samples, in each test set. Given the group structure, it's possible to accidentally have samples from the same group in both training and testing sets within a single fold. Option B also uses 3 splits but increases the test size to 50%, 50 samples, per fold. This almost certainly means many groups will be split between training and testing, violating our requirement. Option C uses 10 splits, each with 10%, 10 samples, in the test set. It's possible to avoid group overlap here, but only with very careful selection, not guaranteed. Option D is the winner, Vamsi. It explicitly defines groups using "NP. Repeat, NP. Arrange, 10, 10, repeating numbers 0 to 9 10 times each, ensuring each group is clearly labeled. With 3 splits and a test size of 20%, the algorithm can keep entire groups together in either training or testing sets, guaranteeing no overlap. This is our primary goal. We need a configuration that strictly prevents any sample from a specific group from appearing in both the training and testing sets of the same fold. This is crucial for unbiased model evaluation. This describes the overall context. We're using a technique called GroupShuffleSplit within cross-validation, a method used for evaluating machine learning models. It involves dividing data into groups to ensure that samples from the same group don't accidentally end up in both training and testing sets of the same fold, which could bias results. This introduces the core problem. We need to choose the correct parameters for GroupShuffleSplit to ensure the condition of no group overlap in train test splits within each fold. This sets the stage. We are given 100 samples divided into 10 groups of 10 samples each. The goal is to find the GroupShuffleSplit settings that guarantee no group mixing across train and test sets per fold. Note the keywords. Guarantee *, no samples from the same group. This emphasizes the need for a configuration that leaves no room for chance and always avoids intermixing. This is option A. Let's analyze this later. Option B will be analyzed later. Option C. This will also be analyzed later. Option D. This will be analyzed later. We have a total of 10 groups. This is important because GroupShuffleSplit works based on these groups to avoid mixing group members across training and testing sets. It is critical to understand how this number relates to the number of samples and the desired number of folds. Each group has 10 samples. This is essential. Together with the total number of groups, it sets the size of the total dataset and how GroupShuffleSplit will partition it. The total dataset size is 100 samples. This is simply the product of the number of groups and the number of samples per group. 10 groups * 10 samples. Group equals 100 samples.